We're going to be talking about covalent compounds. Covalent compounds are molecules made up of a nonmetal plus a nonmetal, and nonmetals are located to the right of the stairstep on the periodic table. These molecules are held together by the sharing of their electrons. They are not donated nor accepted like ionic compounds. In order for covalent bonds to form, the two elements must first notice each other, meaning they need to be pretty close together. Once the two nonmetals notice each other, there will be an increase in their stability or a decrease in the energy between the atoms. This will cause the element to get even closer to each other, and once they reach a certain distance, the bond is made and all possible energy is lost, which causes the molecule to be stable. When the bond is formed, the repulsion and attraction forces of the two atoms are equal, and their potential energy is at the lowest possible point. When atoms form bonds, they release energy and become more stable. The energy can be released as heat, light, sound, or a combination of the three. In order for a bond to be broken, the same amount of energy needed to form the bond must be absorbed, which means the higher the amount of energy was needed to make the bond, the stronger the bond, and the harder it is to break the bond. And as the bond length between the two nonmetals increases, the bond energy decreases, which makes the bond easier to break. And then, break it. Gilbert Lewis was the first to describe covalent bonding using what is known as Lewis diagrams. In Lewis diagrams, dots represent a single non-shared electron and lines represent one shared electron, which are technically written as two electrons to support the octet rule. So the lines located between atoms represent covalent bonds, and multiple lines represent multiple bonds, like double and triple bonds. However, there is nothing higher than a triple bond, so quadruple bonds don't exist. The ultimate goal of atoms in a compound is to resemble a noble gas. In the octet rule, each atom will share electrons with each other in order to each have 8 in their outermost energy level. So 8 valence electrons. The exceptions to this rule are hydrogen, because it's happy with only 2 electrons. Boron is happy with 6 electrons, and sulfur and phosphorus because they can actually hold more than 8 valence electrons.
In order to draw a Lewis diagram, you must first determine the number and type of atoms in a molecule. After that, you can write the E dot notation for each element. This basically just shows the number of valence electrons for that element. Then add up the total number of valence electrons from all the atoms to help distribute them back out after they're arranged. Next, arrange the atoms with the first element in the middle and the other elements radiating off of it. The only exception to this is carbon, so if carbon is present in the molecule, then it automatically goes in the middle. Once the elements are arranged, connect the radiating elements to the center element with the lines to represent a bond, or a shared electron. Then subtract the shared electrons from the total number of electrons, which for the math, the lines represent 2 electrons. Next, distribute all the remaining electrons as unshared pairs, or dots, first to the outermost elements by following the octet rule. If the radiating elements all have 8 electrons, then place the extra electrons as dots on the center element. To draw the Lewis diagram of methyl chloride, we see that we have 1 carbon, 3 hydrogens, and 1 chlorine. To put them in E dot notation, separate the elements and surround them with their correct number of valence electrons. Carbon has 4, all the hydrogens all have 1, and chlorine has 7. Then add up the total number of electrons. Arrange the elements around carbon and draw lines to represent the bonds formed. Since there are 4 bonds, we have already used up 8 electrons, and 14 minus 8 is 6. So we distribute the 6 left to chlorine since hydrogen is happy with 2 electrons and carbon already has 8. For naming covalent compounds, you must name the less electronegative element first, and we'll go over electronegativity more in a second. Then we give the first element a prefix, but only if there is more than 1 atom present. Next, name the more electronegative element and give it a prefix and the IDE ending. Remember that the second element always gets a prefix, and every nonmetal ends in IDE except noble gases. The prefixes are 1 through 10, mono, di, tri, tetra, penta, hexa, hepta, octa, nana, and deca. Electronegativity is the amount an atom pulls on the electron of another atom, and in naming covalent compounds, we want to always name the less electronegative element first, unless we come across an exception. Electronegativity always increases from left to right and bottom to top on the periodic table, with fluorine being the most electronegative element. Now we're going to practice naming some covalent bonds. We see we have one carbon and one oxygen, so since the first element doesn't have a prefix, if there's only one, that makes this carbon monoxide. The next example has 2 nitrogens and 5 oxygens, so since there is more than one first element, this compound is dinitrogen pentoxide. This example has only 1 sulfur and 6 fluorines, so this is sulfur hexafluoride. Remember to name the less electronegative element first.
As covalent compounds bond, attractive and repulsive forces reach stability. Polar covalent is when electrons are shared unevenly and shifted to one side, and nonpolar covalent is when electrons are shared evenly. This diagram just shows you how to find if a molecule is polar covalent or nonpolar covalent, and the difference between ionic and covalent compounds through electronegativities and the difference of an ionic character. Empirical formulas help with the identifying and naming of covalent compounds. What an empirical formula is it's just the simplest form whole number ratio of atoms in a molecule. What chemists identify an unknown substance, they will often start by performing experiments to determine the empirical formula of this substance. Keep in mind that the empirical formula does not indicate the exact number of atoms in a single molecule. Here's an example of how to find an empirical formula. A compound containing nitrogen and oxygen was found to have 8.167 grams of nitrogen and 23.33 grams of oxygen. Determine the empirical formula. First, we find the number of moles of each element by dividing their given masses by their corresponding molar masses. Once we divide to get our moles, we divide each mole by the smallest number from before, which is in this case 0.583. Since 0.583 divided by itself is 1, we have 1 mole of nitrogen, and when we would divide 1.458 by 0.583, we end up with 2.5 moles of oxygen. But wait, we can't have half a mole as a subscript. So in order to get the whole numbers, we multiply the moles of nitrogen and then moles of oxygen by 2. But we don't always multiply by 2, just multiply whichever number works to get all whole numbers. So empirical formula of this problem works out to be N2O5, which is dinitrogen pentaoxide.